Hey, we're going to do a quick overview of the counting test bench and more importantly, how to maybe debug some of the problems you might have. So first of all, the counting test bench is actually just going to run your counting code, the code you wrote for part one. And it's kind of broken down into two parts, one of which you may want to modify. So it has something that's going to generate the clock, and that'll provide the clock cycle to our device under test, our model of our CPU. And you can see here that the clock is basically alternating every 5 units of time. It goes from low, and then it'll be high for 5, and then low for 5, and so on and so forth. So a total cycle time of 10 units of time. And every time it does this, it's actually going to print out a little message in our terminal window down here. And that message will say what the clock cycle time is, and it's also going to be basically looking at the memory mapped I/O, the segments that are available on our display. Currently, it's only showing the segments and not the little LED components. So we'll take a look at that in just a second. So that's one part of it. That's a process that just continues on forever, providing the clock cycle and checking the memory to help us verify our work. The other process in here has some initialization stuff. It initializes the keys to be 0. And then it waits some time, and over time it will adjust the keys. So in my case, I let it run for 1,500 units of time, so 10 clock cycles per instruction, so about 150 instructions. Hopefully that'll be enough time for it to get up to a count of a few things. And then I change the keys. I set the left button, which should cause it to count down. I let it run for 300 units of time, about 30 instructions or so. And then I change the keys all to 0 and let it continue running. Okay, so I'm going to go ahead and run this in my test bench. So I've already used the counting task, counting to create the ROM. And once that's available, I can use the counting test bench. So I'm going to go ahead and run that. And my code was okay. It actually ran the test bench. I didn't have any syntax errors. So first, I'm going to look at the terminal window, and I've selected the output of the counting task. And you'll notice that it shows this count, and if I scroll back to the beginning, scroll back up to the very top here, we can kind of see what happens when we first start doing this simulation. So clock cycle 1, when I do the very first instruction, the displayed value is all X's. It's unknown. Basically, the simulator is working with uninitialized memory. It's digging in and pulling out what it thinks is being displayed on the screen, and it's completely unknown. And then we can see after about 14 clock cycles, approximately 14 instructions worth of time, we get to the point where my code has finally actually initialized that counter, and it's already made its first count because it's starting by counting up. We can also see that my code takes between clock cycle 15 and clock cycle 26, it's all at count 1. So it's taking around 10 to 11 clock cycles for it to go through a full loop where it will update the counter. So we can see as time goes on, the counter actually counts up. So I've kind of verified that my code is actually doing the counting up part. It's showing in hexadecimal just like our display does. And at a certain point, hopefully I get to where I've toggled that button and I see that it is in fact counting down. So this is one place to kind of verify that things are behaving correctly. But the more important thing is to understand the role of the test bench and seeing signals. So the test bench file itself specifies that the entire test bench file is the device under test, and all of that's going to be dumped out to this file that we're viewing. So the test bench itself defines a whole bunch of signals. It's got its own clock, it's reset, it's write data, it's write memory, it's got clock cycles, and it's got this thing called the device under test. So it's got a full module, and then the device under test is our actual RISC-V model, and it's got things inside of it. It has its control unit, it has its data path. So this hierarchy of modules, like the device under test, the two devices that it contains in this test bench itself, and then all of the signals that are contained in those are actually part of this value change dump, this file that's generated here. So it shows things based on their scope of a module. So it shows the test bench module. And when I click on that, I can see all of the variables that are defined in that test bench. So if I wanted to look at the clock cycles, I could click on that and it shows them out here. I'm going to move these a little bit just so we can zoom in and see what's going on. So I can zoom in, I can see individual clock cycles. Now that doesn't really tell me much about what's going on inside of my little simulated CPU. What I really want to know is I want to know what's happening with the program counter so I can see which instruction line I'm on. And I could go back and I could look at my ROM image and try and understand how the code's actually executing. And more importantly, I want to understand individual instructions. So I'm going to open this up. There's my device under test. That's my actual RISC-V CPU, and it's got its internal signals for the instructions. So if I look at this, I can see the actual instruction that's being executed, and I could go through and decode this hexadecimal value and figure out what instruction that was. Or what would be a lot easier here is I could look at the ROM file that was being used, and it provides a side-by-side view of the machine language representation of the instruction plus the symbolic representation that I actually ended up writing. Okay, so this shows me the instruction that's being executed. I also want to keep track of the program counter, so I can kind of see, oh, I'm doing my first instruction, address 0, and since we count by 4s, the second instruction would be at 4, and so on and so forth. In my case, I have a jump instruction pretty high up in my program, so it goes from doing the second instruction to jumping down someplace else. Okay, now in this case, I really want to know what's being written to the memory and read from the memory. In particular, I want to know what's being written and read from that display interface. So if I expand the device under test, I can see that it contains a couple of different modules. It's got the device memory module, the data memory module rather, and then it's got the instruction memory, and then it's also got this I/O device, and then it actually has the components of the CPU, which include the control components and the data path components. Again, almost anything with these little disclosure arrows, that indicates that it's a module. When you click on the module, you can see kind of the individual components of it. So I'm going to look at the data memory module and look at addresses here. And again, it adds that to my trace. By the way, you can right-click on these and have them removed or change their locations and so on and so forth. So sometimes the address is doing something in undefined, something that hasn't been initialized yet, so shows as complete X's. So we can also see when we're accessing things of interest. So if you remember, the LEDs are at address 8004. And the actual keys are at 8008, and the overall display screen is at 8000. So I can kind of pan through here and look at when I'm interacting with the various addresses. Oh, 8000, this is when it's trying to display, change what's being shown on the display. This is probably where my program is doing an instruction, a store word, to store a new value on the display. And I could probably look at what data is actually being written there. So if I look over here, I could add on the right data. And I can see, oh, again, I could check my code and confirm this is where I'm trying to store a value onto my display, and this is where I'm actually taking that initial 1 we saw in the list of values and sending that out to the display. So using this trace, I can also kind of go through and see what's happening with my program instruction by instruction. Okay, so that's really useful, particularly if our instructions aren't behaving the way we want them to. We can actually use this as a means of debugging. In particular, if we get something where everything starts going to uninitialized values, we can use these traces and kind of work backwards, try and figure out what the last valid instruction was. And if we want to, we can even dig down and look at all of the different control signals. So our control part of our CPU, in this case, is broken up into two different units. So I'm going to go ahead and look at this one. So this one has all these different signals that control ALU source, branch, immediate source, jump, so on. So I could look at any particular one of these and can confirm that it's actually doing what I've want it to do for the particular instruction. So when we identify things that aren't behaving correctly, we can use these signal traces. We can try and identify where things are truly going wrong and then work backwards to the source of the problem and examine all the signals involved and try and identify which signal isn't doing what we want. And that gives us enough information to usually go back to the Verilog model and fix things. Okay, so that's kind of a general overview of how to use both the count task and how to use this display to actually debug things. So you might use this both for the count task and also for the count test bench rather, and also for the test bench that does just the general test of a whole bunch of different instructions. So the general purpose test We'll take a quick look at its code here. So the test bench basically loads up the model and lets it run for quite a bit of time. And then it does this check at the end to see if the overall computation that was being done computed the expected value. So I'm going to take a quick look at the original code that is being used here in the ROM. So it's basically just a set of almost all the instructions that our CPU was originally supporting, plus the addition of the load upper immediate that we've added. And basically each of these kind of contributes to a calculation. And at the end, if they've all worked correctly, we get a known predictable value. If any of these end up failing, that final value will not be the correct value or be uninitialized. So if something goes wrong with this, you may have to think through it step by step and kind of check in at each step and look to see whether registers are being updated with the appropriate values. And in that debugging mode, the value change dump, the surfer waveform view, you can actually look and see, oh, in this step is the value 4 being written to register 5. You can actually look at the index of the register being written, confirm that the right index 83 is actually corresponds to register 5. Then you can look at the right data and confirm that it's the number 4. So it is possible to look at all of the details of what's going on and actually figure out where errors may be coming from. Hey, I wanted to do a quick overview of how to use our waveform viewer, surfer, and our test benches in conjunction to try and debug problems with our Verilog. So I'm going to focus on the load upper immediate test bench that's provided here. So first, a quick overview of the test bench and what it's actually doing. So the test bench is going to create this test bench module. The test bench module itself contains a device under test. The device under test is basically a memory, an instruction memory, a data memory, an I/O device, and then your actual CPU model. And it will save all of the signals and information from this test bench module, so all of the signals it contains, and then everything contained in the modules within it, and with the modules within them, and so on and so forth. So this will contain a complete detailed history of everything that happens when we run this test bench. And basically what this test bench is going to do is it's just going to run several load upper immediates. That's the only instruction it runs, but it runs several variations of them. So the rom.txt file has the machine language representation and the symbolic representation of each of these. So it's trying to put A, B, C, D, E into the RA register 1, and then it tries to put FFFF into register 2, and so on and so forth. So this is just testing this instruction over and over and over with a variety of different values. It looks like it's got a total of 10 tests here. And then there should be some expected outputs. We'll check each of these registers to confirm that they contain that value. So I'm going to go ahead and run this test bench with the associated task for it. And I think we'll see down here in the terminal that it points out that it expected to get something and it got a whole bunch of X's. That means it got some sort of uninitialized or unknown value. So we'll dig into that in just a second. So it looks like all 10 of those test cases failed. So we need to do some debugging. So when I go up here to the scopes thing, it shows that overall test bench module. And if I open that up, it shows that, first of all, if I click on it, it'll show all the variables, the signals directly defined in that module. But when I open the little disclosure button, it shows all of the modules it contains. So the device under test, that's actually defined in this particular test bench module. I could open up the top.sv just to back up. The test bench module declares this thing. The device under test is of type top, the topmost module. So I open the topmost module. The topmost module contains our processor module. Then it contains a module for the memory called imem. For the instruction memory, the data memory is dmem. And then our thing that represents our screen, IO. Basically what this waveform viewer is showing me is this whole hierarchy and then all of the internal variables and what they're doing over time. So I'm going to go back to that view. I really want to understand what's happening when I'm doing those load immediate instructions because clearly they're not working. So I'm going to go ahead and expand the device under test, and I really want to focus in on my CPU. This test bench isn't really doing anything with the data memory. I would like to know which instruction's being run. So I'm going to go ahead and click on the instruction variable down here, and it's showing me each of those test cases that it's going through in their assembly language format. Again, I could go back to the ROM file and kind of tie those two together. A, B, C, D, E, 0B7 is this first load upper immediate. And inside my trace here, there it is, the very first instruction being done. I think I'm also going to add in the clock signal here because it'll help me understand the timing of things. So initially, we're going through this initialization process, and the reset signal is asserted for a part of this time. I could add that in too. So we can see the reason we're stuck on that first instruction is because it's being reset. Then once the reset is let go of, we go through that first instruction for a clock cycle. Okay, so I'd really like to understand why this instruction isn't working. I would expect it to, going back to my original thing, I'd expect it to put something in the RA register. So I need to understand what my inputs and outputs to my register are in order to understand what's going wrong. So I'm going to expand my processor model. If you remember, the processor module contained a control module and a data path module. I want to look at this data path module because I want to understand my registers. I'm trying to get this ABCDE stored in a register, and I'm trying to get it stored into a particular register. So I want to look at all the details associated with my registers. So let's see. If I look through all my Verilog stuff, I think I'll find that the register file is this module called RF, register file. Oh, and now I can look at all the individual inputs and outputs to it. So I could look at A3, my input address, and see if that looks correct. Oh, I think that's okay. I think, so we're sending the number 1 in, and if we look up in our tables, we'll find out that the number 1 does correspond to the RA register. So it looks like I'm trying to store things in the right place. What about the data? Is this ABCDE actually being sent in to be my writable data, write data? Let's add that trace in. Oh, looks pretty good. So I've picked where I want to store it and what I want to store. But something must be going wrong. So I guess the third part of storing things in a register would be actually specifying we want to store it using the write enable. And there I found my culprit. I was never actually asserting the write enable signal. So I had the what I wanted to store being sent to the right place, the where I wanted to store it being sent to the registers as well, but I was never actually doing the store it now sort of thing. I wasn't properly configuring my write enable. So now I would go back to my Verilog and kind of work backwards. I know what I'm missing. I need to figure out the right place to actually get it to do that write enable.